EIGRP convergence. In this video, I'm going to talk about one of the most fundamentals and one of the most important topics related to the EIGRP convergence. First, we should know about what is the EIGRP convergence, and after that, we should experience the EIGRP convergence, and finally, we can tune the EIGRP convergence time. Let me to start talking about the EIGRP convergence. This is one of the most important topics about the EIGRP. First, let me to say that here we have two scenarios and we are configuring these two scenarios in this video, and after that we can understand many new terms, okay, related to the EIGRP convergence and also concepts. Look at here, you know that in EIGRP we have three tables in one router. In each router we have three tables. The first table, okay, in the EIGRP is the neighborship table. The first thing that I should say is that after configuration of these two scenarios, we will have neighborship between the connected or directly connected neighbors or routers. Because of that, I'm not going to talk about the neighborship. The neighborship is established, and now we are talking about the next step. You know that the next step is advertising the EIGRP updates, and after that the next table that we will experience on each router is the topology table. Okay, you know that we have many routes for each network in the topology table, but finally we should choose one of them, the best path, okay, with the lowest metric to one destination, and after that the best path means the successor path should be injected to the routing table. Actually, in the routing table we have only the best path, but in the topology table we have the all paths. Okay, you have learned about them. For example, let me to introduce the first example. This is the scenario A. Let me to for example call it the scenario A, and also we have the scenario B. For example, this is scenario A, and then we have another scenario, the scenario B. I'm going to talk about these two scenarios. In the scenario A, as you can see, we have this network. Let me to talk about only one network. For example, 10500. I call it the net A or network A. Okay, you know that in the R1 topology table, let me to write here. In the R1 topology table can be written by TT. TT is the abbreviation of the topology table. Okay, this is not formal, this is informal. Okay, in topology table of R1 for the 10500/24 we have three paths. Let me to show you. Look at here. The first path is from the R1 to the R2 to the R3. Okay. After that, the second path is from R1 to the R3 to the R, for example, 5. And the third path is from R1 from the R4 to the R5. Okay, you know that here for each path we have a metric. The metric of path 1 M1, the metric of path 2 M2, and the metric of the path 3 M3. In most cases we call the metric of each path the calculated distance, or computed in some cases. Calculated or computed, both of them are correct. Computed distance means metric of each, for example, path. This is the, here we have one computed distance, and also here we have another CD or computed distance, and here we have the next CD or computed distance, CD3, CD2, okay, and the CD, for example, 1. Because EIGRP, as you saw in the previous video, okay, is using the bandwidth and also delay for best path selection. Here, as you can see, the best path or the, for example, higher bandwidth links is the path from the R1 to the R2 to the R5. Actually, because that here we have only differences between the bandwidths, we can understand, okay, and we can guess that M1 means, or CD1 means the metric of the path 1 is lower than the CD2, the metric of path 2, and also the CD2 is lower than the CD3. Actually, we know that the best metric is the lowest metric, and the lowest metric is the metric of path 1, R1, R2, R5. Okay, this is R1, R2, then R5. Because of that, we can expect that in the routing table of the router 1, this is the routing table R1 RT, okay, for the 10.5.0.0/24, we are using the pass from the R1 to the R2, okay, and after that to the R5. You know it, and this is not so new for you. But let me to say that after selecting the best pass, okay, in the EIGRP, you know that we are holding the other pass, okay, inside the topology table. Why we should hold the other pass into the, for example, topology table? The answer is so easy, because this is possible the best pass, okay, fail. If the best pass fails, okay, we should find the next pass, and for finding the next pass, okay, we can use the topology table. Actually, we can say in the topology table we have all pass. If the current best pass is not available, we can use the next best pass, the next lowest metric. Now this is the successor route, okay, but assume that the higher pass, the pass from the router 2 failed. Router 2 failed. Now this route is not available. Let me to show you this route is not available, and we can replace this route with another pass. You know that this is so important to, as soon as possible, we are substituting these links with another link. Why? Because now all of the traffic that previously forwarded from this link, okay, now are dropping. Because of that, as soon as possible, we should redirect them to the next pass. Okay, and here we have all pass 1, pass 2, pass 3, R1, R3, R5. Because in EIGRP we have all pass inside the, for example, topology table, it is not so hard to copying the next best pass from the topology table to the routing table. Actually, you know that this link, okay, is not available now. This pass is not available now. Okay, this pass, and we can easily replace the pass 1, the CD1, with the pass 2. Actually, this is the next best pass. Okay, this is the next best pass. Why? Because it has the second best metric or second lowest metric. Because of that, we can use this pass as the new successor. This is the new successor, and we are replacing this new successor into the routing table. Actually, we should remove this pass from the routing table, and then we can add the next pass to the routing table. Because of that, almost in EIGRP, we can say that this protocol is one of the fastest protocol in convergence. Convergence means when the best pass now is failed, how much time takes to replacing the next best pass. And in EIGRP, according to the Cisco documents, maybe this is less than 200 milliseconds. Okay, the Cisco in some documents refer that EIGRP's convergence time, okay, convergence time is less than 200 milliseconds. And let me to assume to inform you about the OSPF. OSPF can take 1 to 2 seconds to converge. Other protocols more than this. Because of that, this is so important that in EIGRP we have the topology table, and we can use the routes into the topology table. When the best pass fails, we can copy them to the EIGRP routing table. Actually, we can say the convergence time in the EIGRP exactly equal to the time that we are copying one record from the topology table to the routing table. It is so easy. Okay, this is the mechanism that we have in the EIGRP. When the best pass fail, we can immediately replace the next best pass, and after that the packets can be redirected to the next pass, to the, for example, this pass R1 to R3, and then, or for example, to R5. This is possible, but this is not always can happen. Why? Let me to show you one simple example. The scenario B. In the scenario B, from the R6 to the 10.9.0.0, okay, we have two paths. Let me to show you. Here we have two paths. The first path is from R6 to the, for example, R7 and then to the R9. This is the first pass from the R6 to the R, for example, 9 and actually to the 10900. Now let me to show you the next pass. The next pass is from the R6, okay, to the R8. This is the first router, and after that from the R8 to the R7. Here we are using the default bandwidth for the interfaces